So the Lewis model was the first model we talked about, and it is the most simple, easiest to understand, but it is an oversimplification of what's actually going on. The more advanced theories of bonding involve quantum mechanics. So these are quantitative approaches that predict a lot of the properties of molecules. They predict bond length, bond strength, molecular geometries, and dipole moments. These are quantitative approaches. But we're going to look at two of these theories in only a qualitative approach. So we're just going to look at the big ideas of it without getting into all the number crunching. And the first one is valence bond theory. In valence bond theory, a chemical bond is viewed as an overlap of two orbitals. So we've learned that electrons hang out in quantum mechanical orbitals that are localized on the atom. And those are the s, p, d, and f orbitals. Okay, so those are the standard orbitals. But we can also hybridize or blend those to form different atomic orbitals. And we'll look at that. So what happens is when two atoms approach each other, the electrons and nucleus of one atom are going to interact with the electrons and nucleus of the other atom. And valence bond theory examines what changes in terms of energy as these approach. A chemical bond will form if the energy of those two atoms is lowered by the interaction. If the energy goes up, they will be repelled and a bond will not form. So it's always nice to look at something simple. Let's look at two hydrogen atoms. So on this graph here, we have energy going up. Here's 0. This is positive energy repelling each other, and negative energy is attracting each other. So here we have the two hydrogen atoms. And they're like in the same neighborhood, a slightly negative energy here. They're a little bit attracted to each other. As they get closer, the energy goes down. They're attracted to each other. There's some overlap in their orbitals. And they get to this point, and we reach a maximum of the negative energy. This is a maximum attraction. And I forgot to mention, on the x-axis, we're looking at the distance between the hydrogen atoms. When they get closer still, there's a repulsion of the nuclei. The nuclei are getting too close, and it's actually they're going to repel each other. And so just like you can imagine, if you rolled a rock or a boulder down, it would, it would end up down here, right? It's going to go to the lowest point. So these hydrogen atoms are, they could move in and out closer and away from each other, but they're going to settle on this distance because that's where their energy is the lowest. That's the most stable place for them. And this area, this distance of maximum overlap is the bond length of a hydrogen-hydrogen bond. And that can be measured. All of this is quantitative, but we're not going to go into the actual numbers. Any questions about that? So that interaction energy is usually negative. It stabilizes. In order for that to happen, we have to have two electrons that can spin pair. When we talked about filling orbitals, we said, well, if you have two electrons in one orbital, they have to have opposite spins so that they can coexist there. Because otherwise you have two negative charges. And, the problem I always had with this was, well, how can you have two negative electrons in such close proximity? Don't they repel each other? Well, if they have the same spin, yes, they do. If the spins are opposite, then they're okay together. So we have to have opposite spins. So usually what happens is we have two half-filled orbitals. We have two half-filled orbitals. They each have one electron in them. They overlap. The two electrons spin pair, and we have an attraction and a bond forms. Sometimes, though, we can have a filled orbital with two electrons overlapping an empty orbital. This is called a coordinate covalent bond. And this happens. And so the 2 electrons in the bond actually come from one of the atoms. That atom's just being really generous. It's like, I see that you don't have an electron to share with me. That's okay, I'll share 2, and we'll form this bond. So as the 2 atoms with the half-filled orbitals approach, the orbitals overlap, and the electrons align so that they have opposite spins. So this is just a summary of what we've been talking about. Valence electrons in an atom reside in quantum mechanical orbitals. The chemical bond happens when we have overlap of 2 half-filled orbitals with spin pairing of those 2 electrons. And the geometry of the overlapping orbitals determines the shape of the molecule. So let's look at dihydrogen sulfide, H2S. I think it would be helpful to have a Lewis structure in here, just sort of for reference. So, Lewis structure of H2S, there's 2 lone pairs on the sulfur. So we look at this 4 electron groups with 2 lone pairs. Vesper theory is going to predict that this has an angle of less than 109.5 between the hydrogen, sulfur, hydrogen. Valence bond theory is going to predict a 90-degree angle. Because valence bond theory says, well, we've got these 2 3p orbitals that are half-filled. Okay, so sulfur has 3 p orbitals. This one is filled, and this one was half-filled. That's going to overlap with the hydrogen. And this one is half-filled, and this is going to overlap with the hydrogen. The hydrogens each have 1 half-filled orbital, and so these guys are going to overlap, and these guys are going to overlap. P orbitals are at right angles to each other. There's one along the z-axis, one on the x-axis, and one on the y-axis. And so if we're just looking at overlap of p orbitals, then we're going to expect a 90-degree bond angle, right? And if you look at it, the actual bond angle is 92. And so you say, well, it's okay, right? 92 is less than 109.5, and valence bond theory predicts 90, but, you know, it's just tweaked a little bit. Do you see the idea here of the overlapping orbitals? Or do I need to draw some pictures? Draw some pictures. I didn't leave myself much room. I'm going to get rid of my Lewis structure, but not like that. So here's the sulfur, and this is not in the same orientation as the picture above, so I hope that's not confusing. But here's a p orbital of sulfur, okay, and it has 1 electron in it. And over here is hydrogen, and it's got an s orbital, and it's got 1 electron in it. They are going to form a bond because this hydrogen with its 1 electron, I just drew it upside down because that's what's going to happen. One of them is going to flip and they're going to pair. This is going to overlap with that one. So we're going to get overlap, and that's going to form the bond. Does that make sense? The 2 orbitals overlap. And so the other, I'm just going to use the ones that are in the plane of the screen. I made that a little too big. So then we can get overlap between hydrogen and another p orbital for sulfur down here. And then sulfur does have another one, another p orbital that's going in and out. And that one is a lone pair. And so that doesn't participate in the bonding. Isn't that a horrible drawing? You have to use your imagination. Yes?
How is this theory different from the other?
Well, it isn't quite yet. It's a little more specific, but it's not really that different. Vesper theory does not look at orbitals at all. And so valence bond theory, we are talking about the orbitals and how you get overlap between half-filled orbitals. But the real difference comes with the hybridization. But any questions about just the idea of how the orbitals are overlapping? That's an important concept. Did I miss? No? Okay. Let's look at another one. So overlap of half-filled standard atomic orbitals worked for that molecule. It was okay. It predicted 90, the actual is 92. That's pretty good. It doesn't work for everything, though. Let's look at methane. So this is what Vesper theory tells us, and this is also what observed reality tells us. If we look at valence bond theory, valence bond theory says, well, it's got to be the overlap between half-filled orbitals. Well, carbon has a full 2s orbital and two half-filled 2p orbitals. So valence bond theory is going to predict that one hydrogen will overlap with this one, and another hydrogen will overlap with that one, and we'll end up with CH2 and a 90-degree angle. But that's not what we see. We see that it makes CH4 and the angle's 109.5. So obviously there's something missing. And what's missing is that the orbitals in a molecule are not necessarily the same as the orbitals in an individual atom. The process of coming together into a molecule changes the orbitals. And so we say that they get hybridized. Hybridization is a mathematical procedure in which you take the standard atomic orbitals, the s, p, d, and f's, and you combine them into what are called hybrid orbitals. These hybrid orbitals correspond better to the actual distribution of electrons. They are still localized between the two atoms, but they have different shapes and energies than the standard orbitals. So in creating these hybrid orbitals, we minimize the energy of the molecule by maximizing the overlap in that bond. They've got a greater overlap now because the electron density is more concentrated in a single directional lobe rather than being on both sides of the atom. Hybridization does require energy. This rearrangement combination of orbitals doesn't happen without a cost. And so you're only going to see it happen when you get an energy payback from the formation of the bond. So what we're going to do in our discussion is we're going to look at the hybridization of the interior atoms, and we're going to assume that the terminal atoms just keep their standard atomic orbitals. That they're not going to hybridize. So general statements. The number of standard orbitals is always going to be equal to the number of hybrid orbitals. So when you hybridize orbitals, you still have the same number of orbitals. You don't gain or lose orbitals. The particular combinations of how those orbitals add together determines the shapes and energies. And what kind of hybridization occurs is whichever one gives the lowest energy. So these calculations, as you might imagine, are pretty involved, and they're way beyond the scope of this class. So what we're going to do is we're going to use Vesper theory to predict the hybridization of the orbitals. And it turns out that works actually quite well and doesn't involve a lot of math. You have to count to 4, right? How many electron groups? 4. Or I guess sometimes we have to count to 8. Scary. Okay, so let's look at the first one here. If we take, for carbon perhaps, We're looking at that methane that the standard valence bond theory didn't work on. So what happens here is we have the 2s orbital and we have 3 of these 2p orbitals. These can be hybridized. You can kind of think of it as averaging, combining and averaging. And we can combine these into 4 degenerate or equivalent orbitals. So we took these 4, where these 3 were a higher energy, this one was lower, and we're combining them together. The average energy of these is pretty much the same, but it's going to be, between. So now we have 4, and they're all the same. They're the same energy. And we name this sp3 because it's 1s and 3p. So sp3 hybrid orbitals. And sp3 you get by hybridizing s and 3p's. Okay, so there's lots of letters and numbers here, but they're trying to tell us what the thing is. Any questions? So what would this look like? So you've got an s orbital, and there are 3p orbitals, and they're oriented perpendicular to each other in space, right? So when we take these guys and we mathematically combine them, we get these 4 equivalent orbitals. And what happens is one of the lobes gets larger and one is smaller. That has to do with the phases of because remember, on a p orbital, one phase is positive and one phase is negative. So when we put these two, combine these together, this is what we end up with. It looks like drumsticks to me. And then these are going to be oriented in space to be spread out as much as possible. When we draw them all together, we tend to ignore the smaller lobe because it's less important. And when you draw them all together, if you're trying to draw that little lobe in there too, it gets really messy looking. And so in the combined, putting them all together in one drawing, we tend to ignore that little piece. Any questions? So when we look at sp3 hybridization, carbon has 4 valence electrons. We hybridized the s and 3p orbitals, and now we see that they will fill individually first with parallel spins. Now we have 4 half-filled orbitals. And we can see how a hydrogen atom with its half-filled orbital could overlap with this one, and another with this one, and another with this one, and another with that one. And so we have our sp3 hybrid orbitals forming a tetrahedron, and then we have the hydrogens overlapping at the end of each of them. And so now we've accounted for the observed geometry and formula of methane, and we see, okay, well, this explains why it's CH4 with 109.5 degree angles. Hybrid orbitals can also accommodate a lone pair. So ammonia, nitrogen, if we look at its orbital diagram, it's got 5 valence electrons, right? So if this is S and this is P. And you might say, well, why not just overlap the hydrogens with those half-filled p orbitals? Why hybridize? What would the predicted geometry be then? What would the bond angles be if the hydrogens overlapped with p orbitals? They'd be 90 degrees, right? But that's not what we observe. What we observe is that the bond angle is 107, closer to the unhybridized p orbital of 90, but not 90, right? It's more like the tetrahedral. So these hybridize into sp3, so that's 4 boxes. So this is sp3, and then the 5 electrons will go in 1, 2, 3, 4, 5. 4 orbitals in a tetrahedral arrangement. One of them contains a lone pair, that's this guy, and the 3 that are half filled can overlap with hydrogen. This guy is going to take up a little more space and push these guys together a little bit. But that's what we end up with. Any questions? We can also hybridize fewer than all of them. An sp2 is 1 s orbital and 2 p orbitals. So here are the standard atomic orbitals, and we're going to take the s and 2 of the p's and combine those. And so those will be degenerate, called sp2. And then we've got this guy left. And so he's just still hanging out here. This is an unhybridized p orbital. So if you take an s and 2 of the p orbitals and combine them, you get this similar drumstick looking shape. But the orientation now is trigonal planar, because there's 3 of them, and they're going to be oriented in a plane. Which makes sense, because these 2 make a plane. And then you average them with this one, and so you get 3 like this. H2CO has sp2 hybrid orbitals. So here we have hydrogen. He's so nice and simple. Oxygen has 6 valence electrons. So in the atomic orbitals, this is what we've got. We've got a pair in the 2s and a pair in the 2p and 2 unpaired, 2 half-filled orbitals. And the carbon, as we saw before, has a full 2s and 2 half-filled 2p's. So the carbon is going to hybridize, and it's going to form an sp2, a set of sp2 hybrid orbitals, and then the p is left separate. 1p remains unhybridized. So then we can stick the 4 electrons in here, and we've got 4 half-filled orbitals. The why does it do that is too complicated for this class. How would you know that it does that? You look at the Lewis structure and the Vesper theory, and that tells you that it makes the sp2, and we'll go into that. Isn't that nice? Okay, so what's going on here? These purple ones are the hybrid orbitals. They're so clever. What do you get when you mix red and blue? Purple. So these are the mixture of red and blue, okay, right? So these are the hybrid orbitals. Here we have hydrogen. It's half-filled orbital overlapping with one of carbon's sp2 hybrid orbitals. Here's the other hydrogen overlapping with one of carbon's sp2 hybrid orbitals. Here's the oxygen. The oxygen is a terminal atom. We're going to assume that it doesn't hybridize just to make things simple. Let's go back here real quick. See what oxygen has? Oxygen has 2 half-filled p orbitals. So those are the things that are available to overlap with carbon here. So here's one of oxygen's half-filled orbitals is going to overlap with the hybrid orbital on carbon, and that's going to form a bond. But now each of the carbon and hydrogen have 1 p orbital that's half-filled, not hybridized. That unhybridized p orbital is going to be perpendicular to these hybridized ones, because this was the x and the z, or the x and the y, depending on how you anyway, sorry, erase that. Carbons, p orbitals, one up and down, one going this way, one going that way. It's the two that are in this blue plane that got hybridized, and this one was left unhybridized. This oxygen has one going up and down that's unhybridized. These guys can overlap as well and form a bond, but they can't overlap end to end. They're not lined up correctly, but they can overlap side to side, and they do. When orbitals overlap end to end, it's called a sigma bond, and when they overlap on the side, it's called a pi bond. And I don't really have any good reason for why they call them that, but that's what they call them, sigma and pi. So pi bond happens when p orbitals overlap side to side. So these two orbitals, half filled, when they overlap side to side. And just like the electron in this orbital is occupying both sides of the lobe, this pair is occupying both lobes. Because this p orbital is really a lot like a standing wave, right? A standing wave. And so the electron's kind of everywhere at the same time. So they overlap side to side. A sigma bond is when they overlap end to end. So sigma bonds are spherical and pi bonds are not. So when we go back to this, here we have this sigma bond, end-to-end overlap, and this pi bond. That's what forms the double bond between the carbon and the oxygen. Because what this molecule is CH double bond O. And this double bond is two bonds. One of them's an end-to-end overlap and one's a side-to-side overlap. Any questions? This sometimes looks like it's two bonds, right? You say, well, that's a triple bond. We've got this one up here and this one and this one. No, this is one lobe and the other lobe of the same bond. Got two orbitals overlapping, that's one bond. So we sometimes label these with a notation that specifies the type of bond. So this one is a pi bond, so we would identify that as pi. And this is the overlap of a p orbital on the carbon with a p orbital on the oxygen. And this is the kind of thing we're going to need to do in the worksheet today. This is a sigma bond, right here, end-to-end overlap. So this is sigma. This is the overlap between sp2 on the carbon and p on the oxygen. And then these bonds are also sigma bonds, overlap between sp2 on the carbon and s on the hydrogen. Valence bond theory is more complicated, but also gives us more insight into what's going on. That double bond between the carbon and hydrogen, there's actually two different kinds of bonds. They are not identical. So in Lewis theory, we have a double bond that always corresponds to one sigma bond and one pi bond in the valence bond theory. The pi bonds are weaker. And when you break a double bond, it's the pi bond that breaks first because that side-to-side overlap is less efficient. The sigma bond is stronger and is with the end-to-end. So the pi bond gets broken first before the sigma bond does. This also helps us to understand why double bonds cannot rotate. Single bonds rotate freely. I'll get some model kits out and we can play with those as well. Double bonds do not rotate, single bonds do. So here, a single bond between carbon and carbon, the overlap, these guys can rotate around and that's fine, and they do. When we have a pi bond here, now we cannot get rotation. And that is very significant when we talk about, especially in organic chemistry. This molecule, because there's no rotation around this double bond, it's important whether the chlorines are on the same side of the double bond or opposite sides of the double bond. What we're looking at here is the same molecules as on the previous slide. So this is CH2Cl, CH2Cl. And then this one is CHCl, CHCl. The difference is there's a double bond in this one, and so it has 2 less hydrogens. When we look over here at the space-filling model, there's the carbon-carbon bond in there, and these guys can rotate around. In the double bond, because of the double bond, they cannot rotate. And so we can have the chlorines on the same side or on the opposite side. These are actually 2 different compounds, and they have slightly different chemical and physical properties just because of how they're connected to each other. We can also have an sp hybridized orbital. One s and one p orbital hybridizing together, so we get these 2 orbitals, and then we're left with 2 p orbitals that are unhybridized. And this is what happens when we have a triple bond. So the sp, just one s and one p, when those overlap, we get 2 hybrid orbitals, and they're facing in opposite directions. And when we show them together, they would look like that. You might say, well, that looks like a p orbital. Well, it does, except we're looking at the large lobe of both, and there's a small lobe inside over here that we're ignoring. So this is actually 2 orbitals. This is 1 orbital. The color helps because it's a different color. So let's look at acetylene. This is HC triple bond CH. Acetylene is going to have sp hybrid orbitals. When we draw the Lewis structure, well, that basically is the Lewis structure. Here's our hydrogen, here's our carbon with its atomic orbitals. When we hybridize these for acetylene, we get sp, and then there's p orbitals, just regular ones. So this hydrogen is going to overlap with one of the sp orbitals, and the other hydrogen is going to, I'm sorry, never mind. I'm getting ahead of myself. When we look at this, the hybridization, each carbon can form 4 bonds. And we've seen that carbon, like almost always, makes 4 bonds, right? But here we only have 2 atoms for this carbon to bond with. And so what's it going to do? I think I'll try my picture first, and then that'll look beautiful in comparison. So here's our 2 carbons, and they've got, this is an sp and this is an sp, and the sps are going to overlap. So this is a sigma carbon sp to carbon sp. The other sp orbital is on the other side, and that's going to overlap with the hydrogen. And so that's a sigma carbon sp to hydrogen s. And then over here, we've got the same thing. And that gives us that linear shape that we're expecting. So the carbon sp overlapping with the s of a hydrogen, the other sp overlapping with an sp from the other carbon. You with me so far? So for one carbon, for each of the carbon atoms, we've taken care of these two. We got those paired up in bonds. Each of these, though, has another 2 orbitals that are half full. So we've got one going up and down. Those are p orbitals. And these can overlap side to side. That's going to be a pi bond between a p orbital on one carbon and a p orbital on the other carbon. So we've got these guys taken care of, and we've got one of these taken care of. There's still another p orbital, and that's the one that's sticking out and going back. And that can overlap side to side. How's that for a messy drawing? And that takes care of that last one. So let's look at the beautiful picture. Here in the purple, we have that sp hybrid orbitals. There's 2 of them for each carbon. One overlaps with the hydrogen, one overlaps with an sp of the other carbon. So there's the other carbon. It has 2 sp orbitals, and one is overlapping with this hydrogen, one with that carbon. Then we have 2 p orbitals that are left over. There's the one going up and down, and there's the one coming out this way. And those are going to overlap side to side. And that's where we get our triple bond. This is consistent with experiment and with VSEPR theory. Any questions? What do you think? Is there going to be rotation around that triple bond? No. In order to rotate around this triple bond, you'd have to break this pi bond and that pi bond. This is not going to happen. Same thing with the double. You'd have to break the pi bond to get rotation. I think this might be a good time for a break before things get more complicated. In the Lewis model, we talked about how elements in the 3rd period or below can expand their octets. And so that's where we got the octahedral and the trigonal bipyramid shapes. Valence bond theory explains this as well. This is hybridization involving the d orbitals as well. And that's why it's only the period 3 and below, because elements in period 2 don't have d orbitals in the 2nd principal energy level that they can hybridize with their s and p's. So we get d orbitals getting hybridized in with the s and the p. And those energies are going to be similar, and so it's reasonable to think that they might hybridize. So here we have a diagram showing 3s, 3p, and 3d. There's 5 3d orbitals. When you're hybridizing orbitals, you can do any combination, but you're always going to start with the s, and then the p's, because that's the next higher in energy, and then the d's. So you could do 1d or 2d or 3d or whatever, but you have to start with the s, then go to p, and then go to d. So we're going to grab the s, the 3p orbitals, and one of the d's, and that's going to give us sp3d. So 1s, 1d, and 3 p's. So we have 5 equivalent degenerate orbitals, and then we've got those unhybridized d orbitals left. When we hybridize these, we get this mess. So that's 5. 1, 2, 3, 4, 5. Does that shape look familiar? We made that with balloons, right? It looks a lot like the balloon thing. These 5 orbitals, hybrid orbitals, are going to arrange themselves in 3-dimensional space to spread out, minimize the repulsions. So if we look at something like arsenic pentafluoride, here's the Lewis structure for it. We see that there are 5 single bonds around the arsenic. Well, arsenic is going to use sp3d hybrid orbitals to make those 5 bonds. Let's look at, because we need to have the orbital diagram for arsenic. So arsenic is 3s2. Let's see. Let's just draw the electron configuration first. It's going to have 3s2. That's not a 3. 3p6, right? Four s2, 3d10. I probably started too soon. 4p3. This is the part we're really interested in. Well, these are the valence electrons for arsenic. Everybody okay with that? I should have just started with the 4s, and I wasn't thinking clearly. So we've got 2 in the s and 3 in the p. And so if we draw that, there's our s, and here's our p. And that's going to predict how many bonds. If we don't hybridize, here we have 3 half-filled orbitals. Those could overlap with other things, and that's going to suggest 3 bonds. But what we actually have is 5 bonds. So this is P, and this is S. Up here, we have d orbitals that are empty. And so it's going to grab one of these d orbitals and hybridize. Then you get 1, 2, 3, 4, 5 sp3d. And now they can each have their own orbital. And each of those can make a bond with another atom. So we've got these 5 bonds, and they're going to arrange themselves in that trigonal bipyramid structure. So these are sigma bonds overlapping between the p orbital on fluorine and the sp3d hybrid orbital on the arsenic. Any questions? Yes?
Are those the 4D orbitals?
Yes. Yeah, so this is 4s, and this is 4p, and this is 4d.
So just move to D because there was 5 electrons and there was 5 spaces.
Yeah, the thing that's hard for you guys is, well, why did it do that, right? Why? How are we supposed to know that? The way you know that is you look at the Lewis structure. Okay, we learned how to do Lewis structures, and Lewis structures accurately predict shapes of molecules, right? And accurately predict number of bonds and all that kind of stuff. And we know to expand the octet here because we want to lower the, what's the name of those numbers? It's not oxidation state. Formal charges, sorry. Formal charges. We want to lower the formal charge. And so we come up with this. I want you to know to do this because there are 5 bonds. And the way you get 5 bonds is to make a hybrid orbital that has 5. S is 1, 3 p's, 1 plus 3 is 4, and then you need a d in there as well to get 5 degenerate orbitals. Does that help? Any other questions? sp3d2, this is 6 orbitals hybridized together. The s, the p, and 2 of the d's. And so we get 6 degenerate orbitals and 3 unhybridized orbitals that remain. And those are going to make this octahedral shape. They're showing these with 3, 3s, 3p, 3d, but it also works with 4 and 5 and 6, but it doesn't work with 2 because there's no T2d orbital to include. So, you know, like, oh, well, we've got those empty rooms. Yeah, let's pull those in and incorporate those. So here's the Lewis structure for sulfur hexafluoride. The Lewis structure shows that there are 6 bonds. There's 6 electron groups. And so that's what tells us we need hybrid orbitals where there will be 6 of them. So we'll include the S and the P's. That's a total of 4. I need 2 more, so we're going to bring in 2 of the D's, and that's the hybridization scheme. So I've got 6 things that are equivalent, right? And they're arranged in space symmetrically around the central atom, and it gives us that octahedral structure. Yes? Are there any F hybrid orbitals? Honestly, I don't know. I kind of think not. The sp3d2 is the largest one we usually talk about. Not that it wouldn't be possible, but I think the problem comes in that you get steric hindrance. You get just not enough space here to get that many things around. To include the Fs, you'd have to have sp3 d5 f1. And that's what, 10? That's a lot. There may be some molecules that do that, but I can't think of any off the top of my head. Any other questions? So again, the labeling of these bonds, this is a sigma because it's end-to-end overlap. Sulfur, S for sulfur. On the sulfur, the orbital that's overlapping is that hybrid orbital, and then there's a dash, and the other atom, well, it's pointing to this one. The other atom is fluorine, and on the fluorine, it's just the unhybridized p orbital. Why isn't it the S? Well, if we look at fluorine, how many valence electrons does fluorine have? 7. And what period is fluorine in? It's in period 2, right? So we've got the 2s and the 2p. 1, 2, 3, 4, 5, 6, 7. Where's the half-filled orbital? It's a p orbital. That's why we know that fluorine is overlapping a p orbital with the sulfur. We're simplifying things and we're assuming that those terminal atoms do not hybridize. In truth, they do a little bit, but not so much that we can't just ignore it. Yes? It couldn't hybridize and end up with 2 half-filled orbitals, no, because it has 7 valence electrons. They would both be full, or 3 or 4, or how many there are, they'd be full. Because you could hybridize, I mean, if you made an sp3, if you made sp3 hybrid orbitals for fluorine, you'd have 4, right? And they would all be full except for 1. So the question would be, well, why would it really do that? But that's beyond the scope of this. Any other questions? It could not include d orbitals, though, because it doesn't have any. So how do we know which hybridization scheme to use? Well, the best answer is you calculate the hybridization and the degree of hybridization to give the lowest overall energy. We're not going to do that. Good enough for Chem 1A. That's all we want, right? We're not striving to be the best and the most thorough. There's many times in life where good enough is good enough, right? You can't be best at everything. So good enough, you look at the electron geometry on the interior atoms. We learned how to do that using Vesper theory and the Lewis model. And that's how you decide what the hybridization scheme is. It's not 100% accurate, but it's good enough for Chem 1A. So here's another one of those tables. So what you're going to do is you're going to look at the number of electron groups and the electron geometry. And the number of groups is going to tell you what the hybridization scheme is. If you have 2 electron groups, you need 2 hybrid orbitals. So you have to hybridize 2 orbitals, an s and a p, to get 2. If you need 3, you have 3 electron groups, you have to hybridize 1 of the s and 2 of the p's, so that you get a total of 3. If you add up the superscripts here, the unwritten 1 and the 2 adds up to 3. For 4, it's going to be sp3. For 5, it'll sp3d. And for 6, it'll be sp3d2. So we're drawing Lewis structures. We're looking at the number of electron groups. The number of electron groups tells us the hybridization scheme. I kind of just said that. Okay, so write the Lewis structure. Use Vesper theory to predict the geometry. Select the hybridization based on the electron geometry. You can look at table 10.3 for reference until you get the hang of it. Sketch the molecule. Start with an interior atom and its orbitals, and then show the overlap with the terminal ones, and then label the bonds. This is the sort of thing we're going to do and practice on the worksheet today. So let's do XEF4. First thing is the Lewis structure. Well, we're going to connect these guys. So we've got xenon, and we've got 4 fluorines. And then we have to look at the number of valence electrons. Xenon has 8 valence electrons. We have 4 fluorines that each have 7, right? So 4 times 7 is 28, plus 8 is 36. So now we're going to put electrons around here. I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I need to put 2 more pairs of electrons on here. Where can I put them? Xenon. Xenon is a big boy. He can expand his octet, and so I can put 1 there, put 1 here, squeeze them in there somewhere. Check the formal charges if there were some different options, and make sure you got your best Lewis structure. So now we look at this and we ask ourselves, how many electron groups on the xenon? 6. 4 single bonds and 2 lone pairs. So I have 6 electron groups. What kind of a hybridization scheme do I need? sp3d2. I need something that combines 6 regular orbitals and hybridizes them. So that tells me that my hybridization scheme is sp3d2. And this is where the drawing gets fun, right? So I'm going to put my xenon in the middle, and 6 things are going to form an octahedron. And so I'm going to have 1 of these going up, up and down. One going up, 1 going down. And then these guys are making that square skirt around the middle. looks like a flower. Let me try that again. Oops. So what I'm trying to indicate, I don't know. I'm trying to indicate that these four in the middle are in a plane. It's hard to draw. Your drawings today on your worksheets are going to be ugly. It's okay. Look, I'm putting this on YouTube. And so then those are going to overlap end to end. Oh, wait a minute. We got to think about this, though, don't we? There's 2 lone pairs and 4 atoms. How do the lone pairs want to relate to each other? They want to be as far away from each other as possible. So I'm just going to choose to make that the up and down. So here's my lone pair. That's a lone pair, and this is a lone pair. Lone pairs take up more space, so they need to be opposite of each other. And so I'm going to put my fluorine in here, and a fluorine in there, and a fluorine in here. What's the shape of this molecule? Planar's right, square planar. So this is a square planar molecule. Square because I've got these 4 in here. Then we need to label each of the bonds. So this bond, is that a sigma bond or a pi bond? End to end or side to side? It's an end to end, so that's a sigma. And it's between xenon. What kind of an orbital on xenon? Well, this one, right? sp3. So xenon is overlapping in sp3d2, overlapping with fluorine. And what kind of a orbital there? A p. Are these other bonds the same or different than this one? They're all the same. So we don't need to label all of them individually. We can just, they're all the same. And then this is a lone pair and a lone pair. Question?
Do you want us to do a fluorine, a key, the infinity sign? Or is it just
Oh, that's a good point. Yeah, I did that wrong. Thank you. Yeah. Okay, I don't know, I had hydrogen on the brain or something. Because this is not a good, this isn't right. Fluorine is overlapping p orbitals. So many letters. So the fluorines are overlapping p orbitals. So my initial drawing there was just not quite right. It was wrong. That's better. Any other questions? Let's do HCN. Well, let's connect these guys. HCN. We have to identify how many valence electrons. 1 for hydrogen, 4 for carbon, 5 for nitrogen, gives us 10. So we've already got 2, 4, 6, 8, 10. Well, that's not going to work. So we have to do some more sharing. So I'm going to take that guy and make him a bonding pair. Still not quite enough. Take this guy, make it a bonding pair. So I got my Lewis structure. How many electron groups around the carbon? 2. What hybridization scheme gives me 2 equivalent orbitals? sp. So this is going to be sp hybridization because there's 2 electron groups. So to draw this, here's my carbon, and it's got s, those are sp orbitals. It's going to overlap with the s orbital of the hydrogen. What kind of an orbital of the nitrogen is going to overlap? Well, maybe we need to draw a little orbital diagram for nitrogen, right? There's S and P. It's got 5 valence electrons. It's going to fill up like this. So what's available to overlap? P's, right? So one of these p orbitals on the nitrogen is going to overlap with the carbon. Is that it then? No, it's not it. We have 2 more bonds to take care of, right? So carbon has this sp hybrid orbital, but it also has 2 unhybridized p orbitals. And so there's going to be one up and down, and then there's going to be one coming in and out. The nitrogen has these 3 unhybridized p orbitals, and so that's going to have a similar thing going on. So we're going to get side-to-side overlap. That's 1 bond of that triple, and then these guys are overlapping. So the up and down is the red is overlapping, and then these that I left in the blue, those are at an angle. They're coming in and out, and those are overlapping sideways as well. So there's my 3 bonds. This red pi bond, the blue pi bond, and this is a sigma bond. So let's label these. So this one right here, sigma or pi? Pi, right? Okay, let me show you something here. If you look at that sideways, does that look like pi? I don't know if that'll help you remember it or not. Those are pi bonds. That's a pi bond, and what's getting overlapped there? On the carbon, what orbital? Just a p. And on the nitrogen, a p. So this is the nitrogen down here. And what the carbon has going on is it has this sp hybrid orbitals, and then it's got its unhybridized, well, let's be consistent maybe and draw that over here. And it's got p orbitals that are unhybridized. So this is carbon. So the sp orbitals are these guys right here. This is sp, and this is sp. This is one p orbital, and this is another p orbital. So what about this blue one here? Your question.
When you write out the bonds, doesn't matter which one goes first?
In terms of whether I put the carbon first or the nitrogen?
Yeah.
I don't think it really does, no. So is this blue bond here, is that going to be the same or different than this red one? It's going to be the same. So that's a pi bond between P on the carbon and P on the nitrogen. What about this one in the middle? That's a sigma bond. So this guy. That's a sigma bond between what on the carbon? sp. And on the nitrogen? Just a p. And then we've got this guy. Sigma. The carbon is contributing what? sp. And the hydrogen has s. Okay? You at least kind of see what we're doing here? And we're going to get some practice while it's still fresh in your mind. And hopefully it'll stick. One more. Carbon dioxide. We've done carbon dioxide so many times, we can just draw the Lewis structure without even really thinking about it too much. What kind of hybridization are we going to have on that carbon? sp. How do we know that? We look at the number of electron groups. 2 electron groups tells us sp hybridization. So the carbon then is going to have sp, and it's going to have unhybridized p orbitals. It's got 4 valence electrons, so it'll have 4 half-filled orbitals. And the oxygen we're going to assume is not hybridized. So that's going to stay with its S and P. It has 6 valence electrons. And so it's going to look like that. So I'm going to put the carbon in the middle. And it has its sp hybrid orbital. Hybrid orbitals, 2 of them. And here's oxygen. What kind of an orbital is oxygen going to overlap with that sp? P. Its s orbital is full. That's not going to do anything. This one's full. It has 2 here. So this is a p orbital of oxygen that's going to overlap. And then over here, and that one's just sticking off the page. It's oxygen. This is a p orbital. What else does carbon have? It has 2 p orbitals left, right? Left, right. So we've got 1 going up and down, and 1 going in and out. So we have double bonds here. So we're going to have this red one overlapping with p orbitals either from this oxygen or from the other oxygen. So let's do this oxygen. So this is going to overlap side to side. And then the other oxygen is going to use its orbital, it's off the screen, that is lined up with the carbon p orbital to form a pi bond. The orientation of these is going to be different. What do we label this green one? Sigma or pi? Pi. So pi on the carbon, what's overlapping with that? P, and on the oxygen, it's also P. Is the red one going to be the same? Yeah, it is. And then we've got this guy in the middle. And what are we going to call that? Sigma carbons sp overlapping with oxygen's p orbital. Okay?